Good morning, everyone. Thank you, Graham, for the invitation to come to QIP. I'm telling you a story about optical atomic clocks, but I want to also justify my presence in this conference. The first question you ask yourself is, what is the connection between an atomic clock to quantum information science? And maybe the answer lies in some of these pictures we have. You're building atomic clock. It's, in fact, is developing the next generation of quantum sensors, which will be necessary to safeguard, to help guide quantum computer. But also, studying quantum interacting many-body systems is part of the game of quantum computing itself. And also, in the end, we all know that the fundamental drive towards searching for new physics is what we want to use a quantum computer for in the future. So there are a lot of discussions, and as I go along. For example, we all know that the number one weirdness of quantum or usefulness of the quantum is really the so-called superposition principle, that something can exist in two places at once, whether it's a coherence between the two spin states, whether it's actually electron itself existing in two places, or whether the atom itself. And because the coherence superposition is so fragile in the quantum, we typically associate quantum with something which is at a very microscopic scales of energy and matter. And that's because our daily experience tells us that as we scale up the system, it's very easy to lose quantum coherence. And that has been the major roadblock for building a quantum computer. How do we put a large quantum systems together with multiple atoms and still being able to taking advantage of a coherent superposition? And these are typical examples of existing at both places at once, or it could be in existing as a coherent superposition between two internal states. So there's currently a revolution going on. That's part of the reason there's excitement for this conference here. And the reason is because we understand that coherence has been driving the quantum revolution, and now the technology is moving to a point where maybe we could control each individual electron, each individual atom, and each individual photons with coherent superposition properties intact, and then bring these individual electron, atom, photons together and actually use that to process information. So this could be, for example, we know that now single photons can be generated, measured without destruction, and manipulated and used as a flying qubit to process information. We know atoms can be put together now one by one in a well-engineered quantum landscape, such as optical lattices and so on. And so really be able to control individual atoms and then bring them together, have them interact. In fact, building atomic clock is very much utilizing this platform here. By understanding the emergence of quantum complexity when you can control individual atoms and bring them together, understanding where the complexity is rising from, and exploring that for quantum sensing is really at the core of atomic clock I'm going to tell you today. And we are now also at the cusp of revolution where you can fabricate new devices for quantum transduction to be able to build a quantum network. And of course, where everybody is excited about here is to solve exponentially difficult problems with the next generation of computing, quantum computer, and so on. But you can see all of this comes back to how we can control quantum coherence, especially when you have multiple atoms, multiple particles come together, start to interact. And that's really at the core of building quantum computer. And this is also where the connection of building atomic clock of next generation measurement capabilities that's connected with quantum computer. Okay, so at the core of this quantum information science revolution, and I think the connection you especially want to highlight between atomic molecular optical physics and quantum information science is the capability of being able to control a quantum system. And once you can control it, you can build complexity and understand where the complexity is coming from the first principle, and then use that quantum systems for computing or for quantum sensing. This is what I'm going to tell you about atomic clock. Once you have quantum sensing, they have the control capabilities of individual qubits. Obviously, that's the building block for quantum information processing, whether it's a digital or analog, quantum simulation, or actual computation. And this also provides the new platform to build new quantum matter. This quantum matter can be useful for building the quantum information, or could it be itself a very useful frontier where we have a new functional material that can be developed. And also using that new quantum material, using this control of individual qubits, using the quantum transduction, we can build quantum networks where individual quantum systems, subsystems can be interconnected to provide expanding capabilities. And that's really the 4 pillars of quantum information science. In fact, I would invite everyone here today to come to a reception this afternoon, actually early evening. The University of Colorado is going to make a big announcement. And if you come with some food to enjoy, we will discuss some of those pillars again at that announcement. So the quantum sensor is not only necessary for quantum computer, but I also want to say this is actually one of the most exciting areas of science right now. In fact, one of the key person in quantum information processing, I don't know if he's here or not, Professor John Preskill. He is coming from, oh, he's actually there. He comes from this field, the standard model and so on. And this is the area he tells me that he still excites him the most, even though you probably know John through his gospels of quantum information processing, right? Error corrections. And to me, this is really the most exciting area of building quantum sensor. Why? That's because our physical theory, the standard model still has a hole. It's been incredibly successful, but we know it is incomplete. It cannot explain dark matter, dark energy so far. We know there's a matter-antimatter asymmetry in the universe, and we cannot explain it out of the standard model. There are experiments going on, and the quantum sensing technology that's connected with quantum information processing probably will lead to a revolution that allows us to really dig deeper. If nothing else, we'll parallel the development of traditional accelerator-based high-energy physics to look for the next layers of secrets the nature is still hiding from us. And these are just some examples. We know from astronomical observations there's dark matter in the galaxy. And also recently, very exciting new development where space-time ripples in the form of gravitational waves can now be observed on Earth. What if we have quantum sensors, such as optical atomic clocks, that can measure the time at the relative precision at the level of 1 part 10 to the minus 21. At this level of precision, you have a clock sitting in the time-space ripple. When gravitational wave comes, if you have 2 clocks you can compare, you'll be able to directly measure the time dilation effect. You can use the clock circling around the Earth, build a quantum network around it, and as the galaxy is moving towards the space of the universe, we may be able to see chunks of dark matter coming through. These are the areas which are particularly exciting for me. Can we make a clock? Just a few years ago, we were talking about clocks at 10 to the minus 14, 10 to the minus 15. And we're talking about 1,000,000 times better. Can we do that? Certainly, we are not there yet. But over the last decade, there have been, thanks to many, many scientists, the field has been moving really fast. Now the clock is entering 10 to the minus 18, and in the very, very near future, it goes into 10 to the minus 19. I don't think it's too far, hopefully in the next 2 decades, and that's not too far, that we will be able to get to that kind of a capability, being able to have a clock being the ultimate connection between quantum physics and gravitational physics and so on. And these are really the connection I want to highlight here. So let me tell you a little bit of a nitty-gritty detail of how to make atomic clock. And this is what Graham told me I should do, because most of you are theorists and you're interested in hearing about the nuts and bolts of atomic clock. So here are the nuts and bolts. Timescales. If you want to have such a lofty goal of being able to use the atomic clock to measure such fundamental symmetry of the universe and so on, let's look at the time scale in the universe. The whole lifetime of the universe is about 15 billion years, and that's 10 to the 18 seconds. On the other hand, if you have a quantum pendulum, which is nothing but electron moving around a nucleus, and if you prepare a coherent superposition of a ground state and excited state, this pendulum is in quantum coherent superposition, is going to swing at the energy splitting between these two orbitals. And that typical time scale, you can associate, of course, it varies, but a typical time scale is a femtosecond, 10 to the minus 15 seconds. So you can see one is the pendulum swinging at a very, very fast time scale, very short time scales. The other one is the universe evolving at a very long time scales. The geometrical mean of these two numbers turns out to be right in the middle of where we feel very comfortable of, 30 seconds. And there's atom, strontium atom, which we use. There are other groups use different atoms and so on. But you can see there's a particular atomic states between ground state and a metastable electronic state happens to be that if you put those two states in coherent superposition, it will live for 160 seconds coherence time. That's a really long time. And in fact, that time scale is comparable to this geometrical mean. What does that tell you? It tells you this oscillator has a tremendous quality factor. If you let it swing, it can swing for 10 to the 17 times without decaying. Or if you slow the swing motion down from a femtosecond to 1 second, and somebody let it go at the beginning of the universe, it's still swinging. That's how high quality factor this clock is. So we want to use that for building atomic clock. And how do we do that? How do we measure such a very long swing without perturbing it? That's the key, right? This is something which is very delicate, very fragile, and very precise and accurate. How do we get that information out without perturbing it? Well, here's a system that we want to measure, and in fact, there's some certainty principle in quantum mechanics, which is very nice. We take advantage of that every day. That is, the energies are discretized, and the space between those electronic states, the energy separation and energy level structure is fixed. This is something unless fundamental constants is changing, unless we have, here's an opportunity for discovery in new physics, unless gravitational physics can somehow come in, change the atomic structure. We know, as far as we know, atoms made in the United States, atoms made in Europe or in Asia, they're all the same. As long as you make your measurements done right, you will achieve the same results. That's the whole point behind quantum standards, is everybody should be able to achieve the same results. But of course, we know the quantum has the more famous principle of the quantum is the uncertainty principle. The uncertainty principle comes that when you put the system in coherent superposition. If the atom is in the ground state or the excited state and you make a measurement, everything is very certain. There's no noise. You can count 100 atoms, 101, 102. There's no noise whatsoever. But as soon as you put the atom in coherent superposition between ground and excited state, and you try to make a measurement, you have to collapse the state from the coherent superposition, and you don't know whether the outcome is going to be ground state or excited state. That's the fundamental uncertainty principle. And that's where all the noise is coming from. So I'm using a little blob, a fuzzy blob, to indicate that when you're in coherent superposition on the equatorial plane, on this so-called Bloch sphere, indicating the ground state pointing down, excited state pointing up, the pseudo-spin half system. When you're in a coherent superposition state and trying to make a measurement, there's a noise. That noise that can be represented by this fuzzy ball. That's a 1 unit of a quantum noise. So in any atomic clock measurement, when you prepare your state in coherent superposition and you try to measure what the state is, you have to deal with this noise. And how do we deal with this noise? We bring out a very precise laser to probe the spin precession along the equatorial plane. Because each spin has this fundamental noise, you want to use as many spins as possible. And this brings the question that, can we prepare atoms in such an orderly fashion where there's no entropy left in the external degrees of freedom, and the only noise really is when you flip the spin? So you can see, if you can realize systems like this, where the momentum of each atom, the interactions between these neighboring atoms, all of these energy scales are quantized, along with internal energy states of the quantization of atomic structure, then the measurement will truly be quantum limited. If you can do that, it's as if you have built a parallel number of those quantum pendulums, and the more you build this, the smaller the uncertainty of the phase noise you will be able to measure. And this is just so-called standard quantum limit. In fact, if you could create coherent superposition among those individual noisy pendulums, the so-called spin squeezing state, then you should actually be able to surpass the standard quantum limit and go even better. And this is at the core of the entanglement of the quantum computing itself. So we need a very good laser to be able to probe this quantum system. And so let me just spend 2 slides for you to explain to you what kind of lasers we develop. Laser, as you can tell, because the speed of light is a constant of nature, length and time, or frequency, is connected through the speed of light. And so therefore, if you have a pair of mirrors that you control the distance between the pair of mirrors extremely well, then the optical frequency that's resonating back and forth between this pair of mirrors is what defines a very stable laser frequency that you can use to probe atomic energy level structure. And to just give you a kind of an estimate of the number that we are talking about, if the cavity, suppose the distance between the 2 mirrors is a meter, and you were able to control the fluctuation of the distance to a fraction of 10 to the minus 16 meters, the fractional length fluctuation is 1 part 10 to the minus 16. If you can do that, the wave that's coming out will be coherent with the frequency at uncertainty at the level of 1 part in 10 to the 16. It's directly related to the length fluctuation. So using that principle, we can build now a very, very stable optical cavity where you can see that this is one of those mirrors, this is another, and we use the crystalline material just to give you a very stiff structure. And we actually do lots of engineering in terms of managing its thermal properties and so on, and such that you can actually build a multiple of such cavities and measure their coherent properties between these cavities. This is the one located in PTB, which is a standards laboratory in Germany. And we made actually two of those. One is sitting in Jella, but we had made a comparison when both of those cavities were sitting at a PTB. The comparison is made such that by bringing two independent lasers together on a common photodetector, measuring the beat signal between the 2 electric fields emitting from these 2 lasers, we can actually observe a beat signal as narrow as 8 millihertz, 0.008 hertz line width. Inverse of that is the coherence time. So this is telling you can have now optical fields with coherence time as long as nearly 1 minute. If I translate that into coherence length, the distance between the moon and Earth is actually just about a few seconds or so. So the coherence is far exceeding the distance between Earth and the moon. If you had to build an interferometer between Earth and the moon, our laser will allow you to go back and forth in this macro interferometer 100 times without losing coherence. It's also getting to the point of where the distance between Sun and Earth is 8 minutes long, and we are catching to the point where the coherent light can span the entire, possibly the solar system. And this can be used for the rulers of the universe. So it can be very useful to keep the satellite distance to be the same and so on. But here we're going to use that for building atomic clock. I want to mention very briefly there's a technology that was developed at the turn of the century, the so-called optical frequency combs. And for that, Professor Ted Hensch and Professor Jan Hall won the Nobel Prize in 2005, connecting basically the coherent spectrum of the visible light anywhere going from VOV all the way to the mid-infrared. Now you can synthesize optical frequencies to be as stable as this one laser that I'm showing you here. So you can distribute optical frequencies throughout the visible spectrum with this kind of fantastic optical phase properties. So now we have lasers, that's reasonably good. We have atoms, I told you there's a quantum pendulum. How do we actually make those measurements? So the first problem you have to encounter is the so-called Doppler effect. The atom is sitting in the lab frame, is moving around. You have a laser field sitting in the lab frame. But if the atom is moving at a thermal velocity, we know if the atom is moving towards you, the energy scale feels, even though initially your laser was tuned on resonance, but if the atom is moving towards you, the frequency gets shifted to the positive, to the blue end, and therefore the energy looks like it's mismatched. On the other hand, if atom is moving away from you, then in the atom frame, the laser frequency is moved down to lower frequency, and now you are no longer tuned on resonance from the red side. So the Doppler effect provides this fuzziness of the resonance, which you won't be able to see, which I was defining to be extremely sharp. But this is a problem that you have to solve, and that problem is actually quite relatively easy to solve, the first order Doppler problem. Because it's a vector, you can always probe from both directions and cancel that. But there's a more fundamental problem, which is a second order Doppler. If atoms are confined in a jar at a room temperature, these atoms are moving around basically at the speed of a few hundred meters per second, like a bullet train. And in that case, we all know that compared to the reference frame of observer who is standing still in the lab frame, the moving clocks of each atom is actually slower. And there's a v-squared term, so that now no longer carries a vector form. It's basically a scalar relativistic effect. Furthermore, the atoms that's at the top of the jar and the bottom of the jar could have a potential difference, since we are all living on Earth. And Einstein told us that if you have a gravitational potential, there will be another time dilation effect, which is a general relativity effect. The time will be different sitting at a different gravitational potential. So if you have a clocks made out of those thermal atoms moving around, not only there's a velocity, but also potential energy difference, and so on, you have made yourself a clock where you can have many, many of those atoms, but each one of them is spinning at a slightly different velocities or speed, so you won't be able to really build a very accurate atomic clock. And it turns out we can learn something from this Doppler effect, because there's actually not Doppler effect just in observation, but there's actually photon recoil, which has consequences on the atomic motion. What is that consequence? Suppose here I pick a laser at this green laser at this frequency that's tuned on atom if the atom is stationary, if it's not moving. But we know the atom is moving. Suppose the atom is moving towards me, and I'm shooting a photon. I'm shooting my laser towards that atom. As the atom moves towards me, the frequency is going to be shifted towards, in the reference frame of the atom, the photon frequency will be shifted towards blue. So what I can do is anticipating that motion, and I'm going to now move my laser frequency towards the red side of the resonance, meaning that I'm giving a frequency that's actually less than the energy splitting of the two atomic states, since the Doppler motion is going to make up for this energy deficiency if the atom is moving towards me. So by moving the laser frequency to be so-called red detuned from the atomic resonance, I will guarantee that when the atom moves towards me, it will actually be able to absorb the photon on resonance and make that transition. This transition, excuse me, this transition, however, has consequences. The momentum of that photon is now being absorbed into this atom. So originally, when the atom is moving along, and when you take that momentum hit from the photon, and the atom becomes stand still. I'm exaggerating a little bit. You actually needed to have tens of thousands of photons scattering to bring the atom to stand still. But that's the very basic principle of so-called laser cooling you may have heard. So the laser cooling was developed in the 1980s and 90s. And these three gentlemen won the Nobel Prize for that. These are the atoms, for example, sitting in your vacuum chamber. You turn on lasers from all 6 directions, counterpropagating. And as soon as your frequency is tuned right, just as I explained in the previous slide, you will be able to cool these atoms down from room temperature to 1 billionth of room temperature in just a few milliseconds. It's an incredibly efficient process. So this is now the atoms are very cold. You can ready to manipulate those, right? These are the quantum objects we want to be making sure that we can hold on to them and do their quantum state manipulation. So how do we do that? You probably heard this year's, last year's Nobel Prize went to Arthur Ashkin. Ashkin and Chu, when they were Bell Labs in the 1970s and 80s developed this optical trapping by basically the idea is that you can focus a laser beam onto a particle. In Arthur's original work, he was really trying to track beads, plastic beads, glass beads. And this has turned into a huge field in biophysics where people are using now these kind of technologies to manipulate DNAs. But here Steve Chu later on adapted this to make optical traps on atoms. And the basic idea is the same. The optical field come in, focus into the vacuum, polarize atom, and you can actually trap atoms at the middle of the laser focus. And the basic idea is here's the energy level structure, but by turning on a fairly strong laser field, you can deform the so-called creating AC stock shift. And this AC stock shift, due to the light, is inhomogeneous in space. Therefore, you can create this kind of a trapping potential where the atoms can be trapped in the middle of that light field. The trap like this, you can see that it's not necessarily suitable for optical atomic clock because when the atom is moving around inside this trap here, the excited state is actually anti-trapped. So when you make energy level measurements, when you make optical clock measurements, the energy level splitting between ground and excited state is actually being modified by the presence of the trap. So your measurement won't be accurate. But turns out you can actually design a special trap. It's optical trap, but playing some tricks from atomic physics, you can actually create traps where the ground state and the excited state can both be deformed in exactly the same manner. And in that case, you can see the atoms are trapped in these optical dipole traps, but as the atom moves around, or you even prepare in the ground and excited state in coherent superposition, the internal degrees of freedom of coherent superposition of ground excited state and the external degrees of freedom, the fact that the atom is moving around in the trap, as long as the two trapping potential is exactly the same, cannot be very cleanly separated. And that's the basic idea of being able to hold onto these atoms, but still be able to make very precise measurements inside those traps. And actually, in terms of building the trap, it's actually really simple. You can have a laser beam, just like, for example, the laser pointer I have in my hand. You can let it propagate in one direction and hit a mirror. It will form a standing wave. We all have done that in the freshman class, optics laboratory. And you can form a standing wave, and those standing waves can be where the intensity maximums are, and you can actually form traps for the atoms. So this looks like a stack of pancakes. Each one of those pancakes can hold tens of atoms or hundreds of atoms, and you can have hundreds of those pancakes, and so therefore you have tens of thousands of atoms. You can use that to build atomic clock now. By holding these atoms in optical traps like this, you start to quantize the Doppler effect. And I want to come back to the Doppler effect because I started talking about the Doppler effect when you try to do this very precise measurements on atoms. This is a typical, even when the atom is cooled down to 1 microkelvin, extremely cold, right, low temperature here, and you put a very precise laser spectroscopy in your lab, you will still see a Doppler broadening due to the fact that the atom is still thermal at 1 microkelvin. The broadening is something on the order of 40 kilohertz, which is a big deal. Remember, I promised you the atomic transition is actually at 1 millihertz line width. So this is many, many orders of magnitude than I want. But by confining these atoms in the stack of pancakes, which I showed, but if you remember from solid state textbooks, the stack of pancakes is nothing but an array of periodical potential. This is what I'm showing, an array of periodical potential, and the atom is moving along that periodical potential. So its motional states is going to be quantized. And what you will see is in spectroscopy is very interesting. If you start just a little bit of a potential, colligating the potential along the way where the atom is moving around, you will see that spectroscopy start to show the Doppler effects to have weird shapes. And this is actually associated, we actually understand the shape completely. How these shapes are coming about is because of the motional quasi-momentums inside this shallow potential of the atom. By making deeper potential, you can start to see very clearly two distinct sidebands shows up. And by the time you go to fairly deep potentials and you do a little bit of a cooling, you can see very asymmetric distribution. The red sideband, the so-called the frequency that's to the red side of the atomic resonance is not disappeared. the blue sideband is quite pronounced. And turns out what's happening is that the atoms being cooled, atoms being cooled down to the actual motional ground state. Once the atom is in the motional ground state, it can no longer be excited. So you can still drive the so-called carrier transition, but you can no longer drive the red sideband because there's no motional states below 0. This is the absolute ground state of quantum mechanics associated with motion. Therefore, this sideband disappeared. This sideband is there because you can always put one phonon back into the system. You can drive from this particular n equals to, this is n equals to 0, n equals to 1. You can go from n equals to 1 to n equals to 2. You put a 1 quanta, motional quanta, back into the system, and that's what this is. So where did the Doppler effect go? Doppler effect went into this quantized form. The original atomic transition is not Doppler-free. The carrier transition, where delta n equals to 0, no longer has any Doppler effect. Also has no recoil effect, and that's because of the trapping potential is so strong that suppress the recoil. So you can now zoom into this resonance and look for this original atomic transitions free of perturbation. And that's really the basic principle where we now can very cleanly separate the internal degrees of freedom, ground excited state, from the external degrees of freedom, which is emotionally quantized, and you can drive in the 1 quanta at a time. And this is basically following the recipe Dave Weiland and so on developed for trapped ion systems. That if you have a single particle and you can control its quantum states, both internal and external degrees of freedom, your measurement can achieve the best measurement precision and accuracy. In our system, we just want to have more atoms rather than just have a single particle. So we put multiple atoms along this one-dimensional optical lattice. This is the picture I showed earlier. You want to have many, many pendulums working in parallel such that you can improve your measurement precision by square root of the particle numbers. And with simple techniques like this, we were able to show now that a clock can reach accuracy of 2 parts 10 to minus 18, and there are clocks that's going to come that's going to get better than that in the next few years. In fact, there's already a clock, Andrew Ludlaw's system has now reached 1.7, 1.8 times 10 to minus 18 accuracy. But overall, it's very much the same kind of a strategy, cooling atoms down, putting them into the optical lattice. You can also do that with trapped ions. The advantage of the trapped neutral systems, you have many of those. So if I summarize what the progress of atomic clock building has been since after World War II, really, after 1950s, as you can see, this is a microwave-based clock that still defines the time at the moment. The SI units of second is defined by atomic clocks of cesium atomic clocks working in the microwave. Optical atomic start to really come on the scene in the 90s, and it has accelerated its performance development over the last decade or so. It's now reaching 2 times 10 to minus 18. And really, if you're summarizing what is other important technologies that's coming out of here, what are the, we call the quantum technologies now, but it's really, most of those are very classical. It's just using classical technology to develop a quantum system that's suitable for exploring these frontiers of a measurement precision and maybe putting entanglement into the system as well. You look for very high quality factor optical transitions. I mentioned that. You have new laser stabilization techniques that allow you to build optical coherence many, many seconds. And you use ultra-cold atoms in lattices where you can have a very large number of atoms, very long coherence times, and very small perturbations. And you use frequency comb to connect different parts of the laser spectrum. Those are underlying technology. And the performance is such that we now currently achieve accuracy at the level of 10 to minus 18, which is corresponding to gravitational redshift of about a centimeter. So if you have a watch, if you're raised by a centimeter, time is changing, and that's the level that modern atomic clock can see. The precision is reaching 3 parts 10 to the minus 19, and then really the goal is we use many-body physics to enable longer quantum coherence and really chasing the goal of being able to develop a clock going down to 10 to minus 21 and beyond. How do we do that? And in the remaining time, I'm going to tell you a little bit of the next generation of clocks that's coming on the scene, which we use 3-dimensional optical lattice instead of 1-dimensional optical lattice. And let me first give you a quick motivation why we want to do that. Suppose you have made your very best clock, and people are not very careful. You're throwing those clocks around, and they come around and they collide. And you're heartbroken because the clock is broken, and it's no longer telling you a very good time if the interaction is not very well controlled. So this is the problem, of course, we know very well from the very beginning, and that's why we build clocks using ultra-cold fermions, because we know when fermions, atomic fermions, if they are cooled down to very low temperatures, how they can collide with each other. Their trajectories are quantized. And we know for fermions, the wave function for the two-particle exchange has to be anti-symmetrized with a negative sign. That means at the very low temperatures, the so-called S-wave collision, where there's no angular momentum, is forbidden. And the lowest order partial wave for the collision to take place with a negative sign in mind is the so-called P wave, where the two particles have to have 1 h by unit of angular momentum for them to circling around. That's the only way you can organize the two particles, two fermions, to collide with each other with an anti-symmetrized wave function. So how do we take that picture into the trapped system where you have, say, one particular slice of the pancake? These spins are confined in the motional degrees of freedom, and they're quantized. Now, if I have multiple of those atoms, and the original goal of doing spectroscopy is nothing but using this very precise optical field to rotate those spins, pointing from the south pole to the equatorial superposition, and then measure the quantum states. But if I let these atoms evolve, if they have some small interactions through the P wave, for example, through the interaction where the total wave function has to be anti-symmetrized, so the spin degrees of freedom can be the so-called triplet, but their motional degrees of freedom, N1, N2, is indexing the motional degrees of freedom of individual spins. That can be anti-symmetrized, so the total wave function is still anti-symmetrized. This is totally allowed, and they will have interactions. It's very weak, but when the measurement precision is very precise, you will measure this very, very weak interactions. And in fact, when you have many atoms interacting together, it provides a spin many-body problem. And it's very much connecting to condensed matter physics to study spin physics. So if we simply just wait, because we have a very long coherence time, even if the interaction energy U is very small, by waiting a long time, you can see these individual quantum fluctuations of individual spins start to become correlated. And you can actually start to recover non-classical spin noise due to the fact these individual quantum fluctuation of individual particles start to be correlated. And this is the correlation that we look for when you want to go for example, spin squeezing and so on. And the consequence for clock is that now the frequency of the energy level between the ground and excited state has a shift depending on the angle of the spin that we process. And so if you are not very careful, you will be making mistakes in your atomic transition frequencies. Even if you are very careful, you say, well, I'm always going to put coherence superposition at this particular angle. The problem is when you have multiple atoms interacting with each other, the interaction can be so strong, it will block how you can coherently excite it. So this is the problem that we want to solve, essentially try to put those atoms away from, so it's kind of a funny way to say they are strongly interacting. But the term strong or weak is always relatively speaking. Even though the interaction energy is very tiny compared to the ordinary daily sense, this interaction energy is less than Hertz times the Planck constant. But if you waited 10 seconds, 1 Hertz worth of energy times 10 seconds is a big number. And that's where I call this as actually strongly interacting systems. You just have to have the patience to wait. So with this comes the next rendition of our system now. This is the so-called 3D Fermi insulating clock, where we want to build, instead of just one-dimensional pancakes, we are now interfering along all 6 directions, all three orthogonal directions in space with the 6 beams. And that forms the so-called 3-dimensional optical lattice. If you loaded the atoms with quantum gas, which is pioneered by, for example, Bose-Einstein condensation was made in 1995 by these 3 gentlemen. Professor Debbie Jing of Jilla unfortunately passed away. She was the one who made the Fermi gas to be possible in 1999. These are all very relatively new developments in atomic physics, but now we are taking advantage of it for building the quantum sensor, such as these type of atomic clocks. And if you use these quantum gas, and in our case, it will be the Fermi gas, it will be following the Debbie's footstep. So you have a Fermi gas and load it into the optical lattice. What's the consequence of that is Fermi statistics, the so-called Pauli exclusion principle, will guarantee if those atoms are extremely cold, they will only load one atom per site. Because we know that if you have motional degrees of freedom is lowered all the way to the zero point fluctuation level, you can't have two identical atoms sitting in the same location. And so this is a scenario we are aiming for. And if you can achieve that, suppose you have 100 rows, 100 depth, 100 column, and you put them all together, you have 1 million cells with holding 1 million atoms. And if you can achieve the coherence time of 160 seconds that I was promising you earlier, then you can actually reach a clock precision of 3 times 10 to the minus 20 with a 1 second averaging. So that's not too far away from 10 to the minus 21. If you waited 100 seconds, you will be at a 3 times 10 to the minus 21. This is really looking very promising. Maybe we don't have a system like that yet. We don't have 1 million atoms confined in 3D lattice. But technology will further develop. If we can really realize systems like this, and if you put a spin squeezing into the system like that, it's no longer really far-fetched to think about atomic clock could reach the level where you can measure gravitational waves. You can use to search the dark matter and really explore the unknown nature of the universe using the atomic clock. And after all, remember, atomic clock is always, whenever Einstein's thinking about general relativities, he always had that little man carry the clock in his mind, thinking about it on the platform, somewhere in the elevator. That guy always had a clock. So the clock is a way to connect the universe. And I think the hope is when clock develops to such level, it will connect quantum physics and gravity. I said it's not quantum gravity, but at least you will have to think, how do you write your Schrödinger's equation where you have spatial coordinates, time coordinates, and they are going to be connected. So the work that we started on this has already resulted some new results. For example, here's a 3D lattice system that we have realized, and if you do spectroscopy on this, it actually shows, I'm showing you the same quantized spectrum of Doppler effect. You can see now the sidebands have 3 peaks, X, Y, Z, because we have a 3-dimensional space now. And again, there's no red sidebands because the atoms are cooled down to the lowest possible energy state in the band structure. So you can see that. Then you can say, well, your atom actually have, the strontium atom actually has nuclear spin of 9.5. So if you are not careful, you could indeed have 10 different nuclear spin states there. And if you have 10 different nuclear spin states, it's possible because different nuclear spin states are distinguishable. So you could actually have multiple atoms loaded into the lowest motional band of the 3D lattice, indicated by these different colors. If that happens, what is the consequence? It turns out the carrier, this is atomic transition if you had only single atoms in there. And you see sidebands. These are the sidebands, not emotional sidebands. Remember, the emotional sidebands is way out there, 50s of kilohertz. These are the so-called interaction sidebands. And you can, again, very easy to understand. If you have fermions, you can have, for example, electronic degrees of freedom, ground and excited state ground can be in the so-called triplet. And then the nuclear degrees of freedom, I use up and down for the nuclear degrees of freedom here, could be in the singlet. And that together, it forms anti-symmetrized wave functions. But because it's a triplet for electronic degrees of freedom, I use a plus sign here. And vice versa. You can have electronic degrees of freedom to be anti-symmetrized, nuclear spin degrees of freedom to be symmetrized. You still have anti-symmetrized wave functions. And you can see these 2 different configurations directly emerge from in your clock measurements. And in fact, by selecting this particular configuration, you have created this entanglement between these 2 atoms where nuclear and electron degrees of freedom is entangled automatically. And it's not just 2 atoms. We can actually do that. We can actually go on, do 2, 3, 4, 5. And this is symmetrized in the electronic degrees of freedom. This is anti-symmetrized electronic degrees of freedom. And all of the peaks collapse onto 1. That's because of the so-called ACM symmetry. That it doesn't matter which nuclear spin state you're on, as long as you have 2 particles, they interact the same energy. And you can actually use a microscope to take an image, and you can actually see the shell structure where the 5 particles sits in the inner core, 4, 3, 2, 1, just like shells of a Russian doll. And so this is a beautiful display of using clock to look for the emergence of multi-atom interactions. So going back to if you have only 1 atom per site, you have this very narrow line width now. And in fact, some of our work shows that the coherence can be all the way up to about 10 seconds or so, atom-like coherence. And this gives you quality factor of 8 times 10 to the 15. But it's not a 160 second that we were discussing. There's some problem here. What is the problem? It turns out the problem is those are fermions in the optical lattice. And if the lattice is too deep, to remove all this momentum coupling, the spin orbital coupling, the lattice has a consequence, a physical consequence to atom. The atom actually Raman scatter or really scatter. They actually spontaneously scatter photons from the lattice such that limits the coherence time from the excited state. So this is the issue. The problem is how do we lower the potential? If we lower the potential, when you drive with a photon, you'll have a spin orbital coupling, and these fermions could move around, possibly moving around, and creating decoherence due to the Doppler effect, due to the interaction effects. So we are using clock to explore many-body physics. And the hope is by understanding this many-body physics using this Fermi Hubbard model. In fact, this is the model people are using to do quantum simulation of quantum magnetism, and use that to really develop a new quantum matter to protect the clock. And I'm going to end my talk, I'll give you those 2 examples. So the first example is how to protect the clock. How do we build a Fermi band insulator clock that this kind of decoherence effect can be protected? So here's an example that when you have, these are the spacing of this 3-dimensional optical lattice. Suppose I just use 2 wells to indicate to show you the effect. The spacing between the 2 wells is A. The wavelength I'm used to probe the clock transition is a lambda clock. This is given by nature. The A is given by, I'm reflecting this so-called wavelength that I use for optical trapping. And remember that wavelength is very carefully selected to give rise to the identical potential of ground and excited state. So if you have 1 fermion, if the potential is not very deep, this fermion can tunnel back and forth between the 2 wells. And because the wavelength of the clock transition and the distance between the 2 neighboring wells is not the same, such that when you drive the transition, the fact that the A is not equal to lambda clock, meaning that when you drive the spin to the coherence superposition on the equatorial plane, you have this extra phase shift. This extra phase shift comes from the fact that you have e to the I Ka. K is equals to 2 pi over lambda. And if A and lambda does not equal to each other, e to the I Ka does not equal to 1. And this is the extra phase shift. It's very easy to intuitively understand the wavelength. Because the wavelength is not the same as A, you have a different optical phase in this well compared to that well. So you can say, well, that's an easy problem to solve. All you need to do is to move the wells apart such that the separation between the 2 wells match with the wavelength. If you can do that, indeed, that's a good solution. In this case, A equals to lambda, then e to the I Ka now equals to 1. Yeah, it's actually a very interesting regime if you think about it. The atom is actually hopping from left to right, to left, to right. It's tunneling back and forth. Light fields comes, and you will see no Doppler effect. Why is that? That's because this tunneling is on 2 discrete sites, and the separation is exactly 1 wavelength apart. So it has no physical effect. The atom can be moving around. The quantum mechanics guarantees there's no Doppler effect. But the problem is, how do you make sure their separation is so precise that exactly matches with the wavelength of your clock laser? Perfect. But it turns, and how do you do that also in the lab? How do you do that in the lab is one way to do it. For example, is instead of having the laser beam going along the mirror and have a radial reflected, you could actually have two laser beams coming like that, and then you tilt the angle like accordion, and that can actually change the spacing between the two optical fields coming and by sine theta. This is something, if you have taken optics class in the undergraduate class, you know, right? Optical fields coming in with some angle theta, bisecting it, you can actually change the wavelength. Not changing the wavelength, changing the spacing of the interference fringes. And this is how you can move the wells around. But you'll have to set this theta angle extremely precisely to be able to take advantage of this factor form equals to 1. And it turns out the problem can be solved very easily if you had two fermions in two wells. And the fermions, first of all, already have the Pauli exclusion principle at play. Second, they'll have some interactions as well. So if this distance between the two wells is roughly right along that, or it doesn't even have to be exactly equal to 1, the fact that these two fermions the spin is being evolved by the optical fields, they mostly follow each other, meaning that even when they are being driven from the ground state to the excited state, or somewhere in the middle in coherent superposition, they always look nearly identical, and they have interaction energies. Therefore, they cannot tunnel. It's already occupied. So during the entire clock excitation process, you will maintain so-called a band insulator, so the fermions won't go on top of each other. They won't be decohered due to the Doppler effect. It won't have interaction effects, and so on. So this is the one way where we can make extremely shallow lattice. Now you no longer need to build a lattice so deep, so individual atoms cannot no longer tunnel. In fact, the lattice can be relatively shallow, and you're using the fact that you have multiple atoms in your system, this many-body system, gives rise to the spatial correlations that coherence time can be guaranteed to be much longer. And that's something that in our lab we are pursuing. On the other hand, if you think you want to actually do interesting physics, instead of doing the clock, which is on the two sides of the same coin, really, you could say, well, what if we do the system like this? What if we actually make the wavelengths purposely to be 1/2 of the interparticle distance, the separation between the wells? What will happen is that now the phase shift is exactly pi between this well to that well, to the next well, to the next well. So by driving it, you created a staggered spin system like what I have drawn on the picture here, using the fact that e to the IKA is now -1. What's so interesting about that? Well, if this well is not very deep, and suppose you make the particle to be able to tunnel, and these two are not identical fermions, so this particle can actually come tunnel over here and tunnel over back, and during that process, it picks up a phase shift due to the fact that when the particle is sitting on top of each other, there's interaction energy. And this goes back to quantum gate. You can use this little interaction energy. The time it is spent on, the time that when it comes in here and it goes back, that amount of time you spend, you can pick up a phase shift. And if you do that along all these entire array of the wells, essentially you can realize this controlled phase NOT gate and realize generating a cluster state along the entire array of the traps. And it's just the same clock system, and you can engineer to do different type of physics that you want. If you write down the Hamiltonian, it looks complicated, but really quite simple. There's a tunneling term that's describing the particles can go from left to the right and vice versa. There's an interaction term describing when the two particles sitting on the same well, how they interact. And there's a Rabi term how this describes how the laser fields are interacting with individual spins. Putting this all together, you can create a complicated phase diagram study, spin orbital coupling of fermions, magnetism, and so on. And maybe for quantum information processing, generating in this three-dimensional system cluster states with a very long coherence time. So with that, I think I'm getting close to the final. I do want to show you that it's not just a fancy talk, that we can actually have some capabilities developed already, being able to image those. For example, this is a 3D lattice, and we can recently implemented the microscope image on top of that three-dimensional optical lattice. And you can see these, it's not individual atom being resolved, but nevertheless getting the resolution is about 1 micron. It's basically 2 cell wide. And you can see the quantum fluctuations of atoms. In the ground state will be the blue, and the excited state will be red, and somewhere in the coherence position will be white. And it's like being able to image every clock in your system. And in fact, we used this for one particular technique where we applied a magnetic field gradient along the three-dimensional optical lattice, and we can take a camera shot, and you can see the fringes, red, blue, red, blue, red, blue. It's because of, due to the magnetic field gradient, the spins are evolved differently under one optical field, and it gives rise to very beautiful stripe patterns. And you can actually study the stripe patterns to study interaction effects if you wish in the future. And I want to highlight, you can actually measure those kind of a magnetic field gradient, measuring these optical coherence, just basically measuring 2 different regions of the optical lattice, the clock atoms, and you can measure the precision at the level of few past 10 to minus 19 at a few hours. So if you have capabilities like this, you can't help but think about what if one day that you have your optical lattice clock sitting here, and your measurement capability reaches the level of 10 to minus 21 and so on. This layer of atoms and that layer of atoms will have a different proper time. What if you create coherent superposition of atoms that can block oscillate back and forth between the top layer and the bottom layer? As they propagate back and forth, they're interacting with their neighboring atoms by dipolar interactions and so on. Meanwhile, the time is not the same time. And this is very different. I want to make sure that it's not, you can say, well, this is just nothing but like your magnetic field gradient. Magnetic field gradient acts on the spin. Gravitational potential is universal. It acts on all degrees of freedom. So that little clock that's being carried by, whether by spin or whether by the internal or external degrees of freedom, they all experience the same general relativity effect. So this is the area will be very interesting to explore the connection between quantum physics and the gravity. And these are the possibilities that we can explore in the future. I think with that, at the end of my talk, I want to acknowledge the contributions of many people have come by through the lab. But currently, Strong Team 1 is led by Toby, Drew, and Colin. The Strong Team 2 is led by Ross, Aki, and Ed, and Sarah have both left. Christian joined us from Germany, and Lindsay, who's shown here. And the stable laser is Eric and John Robinson. Will's picture is not here. And the theory collaborator has been Anna Maria Ray and her group for the last 10 years. And also want to acknowledge collaborators from NIST, PTB, and other theorists around the world on this. Thank you very much for your attention.
Is there a theoretical limit on how accurate atomic clocks can get?
How accurate atomic clock? So if you think about what is the fundamental limit on a clock like this, right? You can say, well, maybe the problem is when the atom is sitting here, a photon comes, and the photon gets absorbed into the atom. The mass of the atom changes. This is like a QCD physics. So this is what it's like emit a gamma ray photon, and you go to a different nuclear state. Here we are talking about incredible precision. Say suppose you go to the 10 to the minus 25. You'll be able to weigh the mass of a single photon by doing that, by just measuring clock shift. But that's not going to be the limitation. That's just an effect that you can measure. I fundamentally think that the limitation will come one day when the universe is not a quiet place. You have gravitational waves. We celebrate gravitational wave detection, but it's everywhere, right? There's a stochastic field of the universe because there are so many gravitational waves. Fundamentally, that will be the end of the clock. I don't think we will get there anytime soon. This might take 100 years to get there, but there will be clock that will be there, and every one of them. Professor Dan Klappner, one of the pioneers in the field, made this very interesting comment. In the 200 years ago, the Royal Navy of the UK, the British Royal Navy, when they were sailing out to the ocean, it was difficult to have a clock carrying on the ship because it's a rocking ocean, rocking sea, right? The clock, pendulum clock is not going to work. So they invented the clock which you can wear, chronometer. And eventually, the atomic clock like this, as you develop further and further, the entire universe is a rocking ocean with the gravitational waves. If you get to that point, isn't that just amazing? That all these kind of discovery can't be quiet anymore. The time is completely relative. I can only say that. I don't think we'll ever get to the Planck time scale because that's just way beyond. The universe would have to die first.
We have one more question right here.
Question and a comment. First comment, ion-based clocks have reached the 10 to negative 18 level, I think, already in Pike's group. I don't know exactly how to say his name. But the second question I have is, so you showed
accuracy or
yes,
measurement precision?
I remember accuracy, but I could be wrong.
Sorry?
So I believe it was accurate. Not quite as good as yours, but 10 to minus 18.
I mean, people certainly, even here at Boulder, they are ion storage group. They haven't published the paper yet. They are evaluating down to 9 times 10 to minus 19 systematic effects. Yes, these are as I said, these are the developments that's ongoing, very exciting. Will go on. Like for example, in our lab, we recently were measuring against between 2 clocks, and you can average it down to 4 or 5 times 10 to minus 19 in just 1 hour. So in 1 hour, you can check systematic effects at the mid 10 to minus 19 level. And surely, with that kind of a measurement precision, you will improve on the accuracy.
Yeah, just a question. I could be completely off on bandwidth here or timescales, but you have to change the lambda for your clock. You have to lock it basically, right?
Change your what?
The wavelength of your clock laser is locked to the atomic transition.
Yes, that's correct.
So, but you also have to match that spacing in your lattice. So are you dynamically changing theta as you're changing the clock laser?
Oh, you're talking about, so there's 2 different wavelengths here, right? There's a clock laser, which is probing the actual transition. There's a wavelength which you use to trap atoms. And that wavelength is especially designed to give you the small amount of AC stock shift, differential AC stock shift between the ground and excited state. And we actually using the technology of frequency comb to connect these 2 optical frequencies together such that the wavelength that's used for optical trapping is actually referenced to the optical clock itself. So it's all bootstrapped together.
Let's. I think maybe it's time for us to go have a cup of coffee and thank June again.